So today we're going to talk about how we can measure evidence with something called a p-value. So to do that, we're going to look at this example. Does drinking tea boost your immune system? So for this study, they had participants that were randomized to drink either 5 cups of black tea or 5 cups of coffee every day for 2 weeks. So they were going they're trying to see if tea helps your immune system, but tea also has other things in it, like lots of caffeine. So they want to make sure they're kind of comparing apples to apples. So they had group 1 drink this black tea. We had group 2 drink the coffee, which does not have the L-theanine, which is supposed to help your immune system in it. And then at the end of 2 weeks, then we measured everybody's immune response. So after 2 weeks, blood samples were exposed to an antigen, and then production of this interferon gamma, which is an immune system response, was measured. Okay, so our explanatory variable was tea or coffee, and our response variable was the immune system response. So explanatory variable, tea or coffee, that's going to be a categorical variable. My response variable, immune system response, this was a quantitative variable. So I'm looking at, if you think about our little chart, then we're looking at a difference in means. So this is a document that kind of walks you through how to do a hypothesis test. And it covers sections 4.1 all the way through 4.3 with an example and everything in here. So this might be a handy reference guide as you're doing your homework. But right at the beginning part of that, then we have this little chart here. And in the example that we're looking at right now, we decided that we had 1 quantitative, 1 categorical, right? Our response variable was quantitative. The explanatory variable was categorical. So if I look, that kind of blocks out this line on my chart here. I can see that I'm going to need to define 2 parameters, mu1 and mu2. And when I write my hypotheses, null hypothesis is going to be that mu1 equals mu2. And then the alternative is going to be that mu1 is either greater than, less than, or not equal to mu2, depending on the wording of the problem. I can see that my sample statistic is going to be x bar 1 minus x bar 2. And the types of graphs that would be good for this type of data would be side-by-side box plots, side-by-side histograms, or side-by-side or stacked dot plots. So anyway, you might want to check this out it's in this week's folder in StatKey, because it has all these things along with a nice example and even showing you how to do it in StatKey and everything. But the chart, I think, is really helpful. This is something that I would put on my cheat sheet if I was you guys. All right, so back to our problem here then. We want to find out, does drinking tea actually boost your immunity based on this study? So a couple questions first, and I'll put up the poll for this one here. If the tea drinkers have enough higher levels of immune system response that we can conclude that drinking tea rather than coffee caused an increase in this aspect of the, oh wait, I'm saying the question wrong. If the tea drinkers, if in the end we see a big difference between the tea drinkers and the coffee drinkers, can we conclude that the tea caused the increase in the immune response? So A for yes or B for no. Right, interesting. We started off by getting a lot of people that were choosing the right answer, and then kind of split in the end here. We did end up with more people choosing A for yes, and A is the correct answer. So remember, how do we determine whether or not we can draw a cause and effect relationship? Well, it directly relates to the type of study that we're doing. If the explanatory variable is randomly assigned because we're doing a randomized experiment, then yes, we would be able to draw cause and effect conclusions in the end. And that's what we're doing here, right? We have these researchers. The researchers are controlling what drink the subjects are drinking, whether they're drinking tea or whether they're drinking coffee. All right, so here's our 2 parameters. So we could call them mu1 and mu2, or you can call them something with a subscript that's a little bit more meaningful. So I called mine mu-T, which would be the mean immune system response after drinking tea, and then mu-C, which is the mean immune system response after drinking coffee. And remember, these parameters represent not just our sample drinkers here, but the mean for anyone who would drink 5 cups of black tea a day, or anyone who would drink 5 cups of black coffee a day for, well, it doesn't have to be black, I guess, 5 cups of coffee for 2 weeks. And we want to know, does drinking tea boost immunity? So what should our null hypothesis look like for this test? You could type something in the chat window and try to do your best you can with the symbols that we got going on here. All right, good. I like how every single person that responded did something different for the mu. It's kind of funny. So remember, for our null hypothesis, then we always have the equal sign. And since we're comparing 2 groups, that makes the null hypothesis pretty easy, because we're just going to say the 2 groups are equal. So mu t equals mu c. And you guys didn't put this in the chat window, which is okay. But remember, when you're actually writing out the hypotheses here, you're going to use an H naught symbol and then write the mu t equals mu c. And I already gave away the answer for the alternative hypothesis here. But why did I choose a greater than sign here for my alternative hypothesis? What's the key word in my research question up here that would let me know that I should have used the greater than was the right symbol rather than less than or not equals to?
Boost?
Yeah, boost, right? Boost, we're thinking that if you drink tea, you're going to have better immunity. So we think that the mean for tea drinkers is going to be greater than the mean for coffee drinkers. So boost was the code word here in this one. Okay, so step 1, we've written our hypotheses. Next, we're going to collect the data. Once we've collected our data, what's the very first thing that we always do with our set of data? Remember, I've got this data, and first I just want to see what kind of information is there in my sample. So the very first thing that I would always do is graph it. Exactly. And what kind of graph would be good for this type of data? Here, I'll throw up the poll again. All right, we got an interesting mix of answers here. But the most commonly chosen answer was the side-by-side box plots, which was the correct answer. So again, if you have this chart handy, once you decide what row you're on, everything comes from that row. So we decided we're on 1 quantitative, 1 categorical. So we knew there was 2 parameters we had to define. We knew how to write our hypotheses. And we can see that side-by-side box plots, side-by-side or stacked histograms, or side-by-side or stacked dots plots would be the best option for graphs here. And so here is a side-by-side box plot for the data from this study. And looking at this box plot, you can see that in our sample, the tea drinkers did have a higher level immune response than the coffee drinkers. And once we've graphed the data, then we can go ahead and compute some numerical summaries. Okay, and again, if I look back at my chart here, okay, the numerical summary that I want to use, or in other words, my sample statistic that I'm looking at, is going to be X bar 1 minus X bar 2. So I'm looking to find the difference between the coffee and tea drinkers here. So I took the X bar for tea minus the X bar for coffee. So that was 34.82 minus 17.7, which equals 17.12. Okay, so this is my sample statistic from my actual sample that I have going on here. All right, so looking at our sample data here, in the sample, clearly there was a difference between tea and coffee, right? But what would happen if I were to do this again? Would I get the exact same results? No, I wouldn't, right? If I took another sample and did the same study again, I would not get the exact same results. So is there really a difference between tea and coffee? Or is this difference that we're seeing in our sample, could it have occurred just due to chance? So there's kind of 2 plausible explanations for the difference that we're seeing in our sample. So One explanation is that the alternative hypothesis is true, and tea drinkers really do have a higher immune system response than coffee drinkers. The other explanation is that the null hypothesis is true, and just due to random chance, then we ended up seeing this difference in our sample. So it just turned out that people who already naturally had better immune system response ended up in the tea group. And so there really isn't a difference between tea and coffee. It just happened due to chance that we got these, better people, better immune system people in the tea group this time. So one of these things, these are two plausible explanations for seeing that difference in our sample data. And we have to decide which one of these seems the most plausible based on our data. So our goal is to determine whether the null hypothesis and random chance are a plausible explanation given the observed data. And in order to look at that, then we have to figure out what kinds of statistics would we get just by chance if the null hypothesis were true. Okay, so we have to decide if it's possible that or how likely it is that we would get sample results that were this big if the null hypothesis was actually true. So to do that, to figure out what kinds of statistics we might get due to chance if the null hypothesis were true, we're going to construct something called a randomization distribution. So let's write down what a randomization distribution is, and then we're going to kind of show how we construct a randomization distribution, where it comes from. So a randomization distribution for hypothesis tests is going to be a very similar idea to a bootstrap distribution for confidence intervals. So first of all, a randomization distribution is a collection of statistics from samples simulated assuming the null hypothesis is true. All right, so the whole point of doing this randomization distribution is going to be to show us what kinds of statistics would be observed just by random chance if the null hypothesis is true. So it's going to show what kind of statistics would be observed just by random chance if the null hypothesis were true. And these randomization distributions, they're going to be centered at whatever we said the parameter was in the null hypothesis. So centered at the value of the parameter given in the null hypothesis. All right, because basically, we have these two hypotheses here. We have the null hypothesis and the alternative. Okay, and we said the alternative hypothesis is what we're trying to prove or find evidence for. This process of hypothesis testing is kind of a lot like our legal system, in that in the legal system, you're innocent until you're proven guilty, right? Until we have enough evidence to convict you. And it's going to be the same type of thing with our null and alternative hypothesis here. We're going to kind of assume the null hypothesis is true until it's proven, or we have enough evidence to reject it and conclude that the alternative is true. So this randomization distribution is going to help us figure out, okay, how much evidence do we have against the null hypothesis? And then we're going to have to use that. When we get that measure of evidence, we'll have to use that to decide whether or not we're going to reject or fail to reject the null hypothesis. Okay, just like the jury in a court case has to look at all the evidence that's given, and they have to come down to a verdict and say, okay, are they guilty or not guilty? So this randomization distribution is going to help us measure the evidence, because it's going to show us what types of statistics we could get purely due to chance if the null hypothesis was true. Okay, so let's look at how we would actually simulate these samples. We said that it was a collection of statistics from samples simulated, assuming the null hypothesis is true. Okay, so we're going to show how are we going to simulate samples taken assuming the null hypothesis is true. And this is how we're going to do it. Okay, we start by doing our actual experiment. So in our actual experiment, we started with all these people. We randomly assigned all of our subjects into two groups, the tea group and the coffee group. All right, then we told the tea group, drink 5 cups a day, every day for 2 weeks. We told the coffee group, drink 5 cups a day, every day for 2 weeks. And at the end of 2 weeks, we measured everybody's immune system response. So here's all the little numbers in there that represent all these different people that were in the different groups and what their immune system responses were. Okay, and we were able to calculate our sample statistic by taking the mean of the tea group minus the mean of the coffee group. Okay, so this is our original sample statistic right here, the 17.12. So this is the difference we saw in our sample. Okay, now we want to see how likely it would be to get this sample statistic, 17.12, purely due to chance. And in order to do that, we need to simulate some samples assuming the null hypothesis is true. Oh, I guess I'm getting ahead of myself here. Okay, so there's 2 plausible explanations for this. Either tea boosts immunity or we got it due to random chance. So we need to figure out what's going to happen or what could happen just due to random chance. Okay, so to do that, we're going to simulate samples assuming the null hypothesis is true. Okay, if the null hypothesis is true, and the immune system response is the same for tea drinkers and coffee drinkers, then it would not have mattered which group people were assigned to. They would have still had the same immune system response at the end of 2 weeks. If there's no difference between tea and coffee, then they would have gotten these same measurements regardless of what they drink. So in order to simulate that kind of scenario, we're going to take all of our values, okay, from our original sample, kind of put them back together here, and then we're going to re-randomize, okay? So I'm just taking, regardless of what group people were in to begin with, I'm going to randomly assign the values to treatment groups. Because this says, hey, it really didn't, you know, if the null hypothesis is true and there's no difference between tea and coffee, then it really wouldn't have mattered what group they were in anyway. So we're just going to take everybody, reshuffle them into 2 groups, and then we're going to find our simulated sample statistic from our new simulated sample. Okay, so in this case, for this particular one, then I got negative 12.3. So this one is a simulated sample statistic. It didn't come from my original sample. It came from my simulated re-randomized sample going on here. Okay, so on my randomization plot, this would be 1 dot on my randomization plot. And I'm going to do this lots and lots of times so I can see, okay, what kind of values would I get purely due to chance if the null hypothesis was true. When I do it lots and lots of times, which we're going to have StatKey do it for us. Like I said, look at this. This looks very, very similar to a bootstrap distribution. It looks very, very similar to a sampling distribution. We're going to talk about the differences between the 3 different distributions here eventually. But this one, these are all sample statistics that came from simulated samples. The samples were simulated assuming the null hypothesis is true. So my null hypothesis was that mu1 equaled mu2. So you can see that the center of this randomization distribution, it centers on the value under the null hypothesis. So if mu1 equaled mu2, then the difference between those would be 0. So this distribution is centered on the value under the null hypothesis. Okay, we're going to do this lots and lots of times. All right, so this randomization distribution, again, it's a collection of statistics from samples simulated assuming the null hypothesis is true. And these are all things we wrote down earlier, but the randomization distribution is centered at the value of the parameter that's given in the null hypothesis. So once we know what kind of statistics we would see purely due to chance, if the null hypothesis were true, then we want to figure out, okay, well, how likely is our observed sample statistic going to be? How likely would it be to occur due to chance? Okay, so how extreme, in other words, is our observed sample statistic? Okay, the original sample statistic is what we're talking about here, the observed sample statistic. So remember when we did the original study with the people who actually drank tea, people who actually drank coffee, then we got a value of 17.12. So you can always see that in StatKey up here in the upper right-hand corner. And so we want to figure out, okay, how likely would it be to get 17.12 if the null hypothesis is true? Okay, so to figure that out, I'm going to look down here on this axis, and I'm going to try to find the value of my original sample statistic, which in this case is 17.12. So 17.12 is over here. Okay, so how likely would it be to get 17.12 or more? Does it seem like it would be really likely, somewhat likely, or not at all likely? What do you guys think?
Somewhat.
Okay, somewhat. Yeah, so these were all simulated assuming the null hypothesis was true. There's some values that are out there. There's not a lot of values that are out there. So somewhat likely meaning, yeah, it could happen, but it's not like really likely, right? A really likely value would be something in here, maybe 5 or -5, something like that. You can see there's lots of values in that range, but 17.12 over here, a little bit less likely.
Professor, real quick. So why was the null 0?
Okay, so the null was 0 because, so the null hypothesis was mu1 equal to mu2. So if I was to like get mu1 and mu2 on the same side, that would end up saying mu1 minus mu2 equals 0. So
Okay.
if mu1 equals mu2, then the difference between them is 0. Does that make sense?
Yeah. So the center of the distribution will always be 0 for this.
It'll always be 0 when you're comparing two means or two proportions. When we do something like a test of one mean, like yesterday, one of the examples we looked at, I think, was number of hours of sleep a night, I think, for college students. And we wanted to see if that was less than 7. Okay, so in that case, then 7 is the hypothesized value. So our distribution would be centered on 7. So it's always going to be centered on whatever the null hypothesis says. All right, so we kind of eyeballed this and we're like, okay, somewhat likely, but somewhat is not a very black and white kind of term, right? We need a more formal way to measure how extreme a statistic would be if the null hypothesis was true. Okay, and the way that we're going to measure that is with something called a p-value. So we're going to write down some things about the p-value, and then we're going to kind of show how we would find the p-value and hopefully explain a little bit more what it means here. So p-value, first of all, it's a probability computed assuming the null hypothesis is true. So it's the probability computed assuming H naught is true, the null hypothesis is true, that the sample statistic would take a value that is as extreme or more extreme than that actually observed. All right, and if you remember that one way that we can find probability is to look at the proportion of times that an outcome would occur in a very long series of repetitions. So another way to look at the p-value is that it's the proportion of samples that, when H naught is true, would give a statistic as extreme or more extreme than the observed sample. All right, so we're gonna talk about how to find this p-value. Once we find our p-value, okay, a p-value is a measure of how much evidence we have against the null hypothesis. So the smaller your p-value, the greater the evidence against the null hypothesis. Okay, so smaller p-value means more evidence against the null hypothesis. Okay, so let's think about this for just a second, kind of review probability here, okay, because, oops, oh, I forgot I had to erase everything because I moved to the next slide, okay, but we said that p-value was a probability, okay, and so let's think about how we find probabilities, right? If I have 10 cars, 4 of them are red, what's the probability that I choose a random car and I get a red car? How would I figure that out? We talked about probability recently, so this shouldn't be too hard. Like what's
Divide 4 by 10.
Yeah, 4 divided by 10, right? Okay, I just take the total number of red cars divided by the total number of cars. So that'd be 4 over 10 or 0.4. Okay, so that's how we figure out probabilities, right? So we're going to do the same thing to figure out this p-value probability here. So this is just the explanation of how we're going to do it in StatKey. I actually, if you printed out the notes page, this is already in your notes, so you don't have to go writing it down exactly. But what I would like you to do is I'd like you to go with me and let's look at this inside of StatKey. So unfortunately, this one is not preloaded in there. So in StatKey, we're gonna have to go to the place where we download the data set. So I don't know how you guys get there when you're doing it on the homework, but I always click on the name of the textbook here. And then I click on data sets on the side. And then I click on data sets for the 3rd edition. Okay, and this one is called ImmuneT. So I have ImmuneT, and I'm going to download the CSV file. Actually, I downloaded it earlier, so I'm not going to re-download it, but you guys should download the CSV file. All right, everybody find this page. So we're just in the data sets page. We're downloading the ImmuneT data set because that's going to be the data from this study that we're looking at here. Once you download that, then we're going to go back to StatKey. So here I am on the StatKey homepage here. All right, and in StatKey, when I'm doing a hypothesis test, I'm going to be in this last section over here where it says randomization hypothesis tests. All right, and for this one, okay, so again, think back to our chart here. Remember, we said we're doing one quantitative, one categorical, so everything that we're doing is going to be on this line here. I've already written my hypotheses. I've done all that kind of stuff. But if you're having a hard time figuring out where to go in StatKey, then if I look over here, it says one quantitative, one categorical. So that would follow and lead me directly to doing a test for difference in means. So if you're ever like, I can't remember exactly where to go, okay, figure out how many and what type of variables you have, and then follow that all the way over. And that's going to put you in the right place for your hypothesis test. Okay, so I'm going to click on, so I'm in the randomization hypothesis test section, and I'm going to click on test for difference in means. All right, now I have to put my data in. So remember to put the data in, you're going to click on upload file, and then you got to find your ImmuneT data set wherever you downloaded it to. Mine automatically goes to my downloads folder, but I don't know what it does on your computer. Then you have to tell it which variable was categorical and which one was quantitative. So our quantitative variable was the interferon gamma, that was that immune system response number. And then the categorical variable was whether or not they drank tea or coffee. So make sure that the interferon is the green and the drink is the orangey yellowy color. What do you think? Is that orange or yellow? My kids are always like fighting over whether or not school buses are orange or yellow. This is kind of the color of a school bus.
School buses are yellow though.
That's what I say too. But then some of them are like, no, they're orange. I'm like, no, they're yellow, but they're like a orangey looking yellow. But I don't know. My kids play this game in the car where they can smack somebody if they see a yellow car. So basically, yeah, every time we see a school bus, it's like, sometimes it's up for debate. But there are some rules about school buses because obviously you're going to see a ton of school buses next to a school when school's getting out. So you're not allowed to smack anybody. If you can see a school and you see a school bus, you can't smack anybody for the school bus. So yeah, exactly. Classic game. My kids love it. It's so funny now because now even they play it so much that like now when I'm driving in the car all by myself, like all of a sudden I'll see a yellow car and I'll like reach out to smack somebody and nobody's there. And then I'm kind of embarrassed that I'm an adult and I'm still playing this game in my car by myself. All right. Okay. So once we've uploaded the data on here, so again, look over in this upper right-hand corner and you can see all the information from the original sample. Okay, this is similar location, similar idea to what we had with bootstrapping and also with sampling distributions. So upper right-hand corner, original data, the original sample. So we can see that from my original sample, the difference in those sample means was 17.12. We can see that, let's see, the tea drinkers had 11 people in their group and the coffee drinkers had 10 people in their group. So there's 21 people total. All right, so now we're going to create this randomization distribution. So remember how we talked about how we're going to take everybody, put them back together, re-randomize and sort them into two groups and then calculate our sample statistic from that sample that was simulated, assuming the null hypothesis is true. That is exactly what StatKey is going to do, only much faster and more efficient. Okay, so we're going to click on this. If you want, you could just click on it. Just click on it once for now, so that you can actually see all the dots there. Okay, so each one of these dots is a sample statistic from a simulated sample, a sample simulated assuming that the null hypothesis is true. And because this involves resampling and everything, yours is going to look a little bit different than mine does, but they should be somewhat similar. Okay, so now let's think about this idea of a p-value, okay? We said a p-value is a probability calculated assuming the null hypothesis is true, that we would get our sample statistic or something more extreme, okay? So the randomization distribution was already constructed assuming the null hypothesis is true. So we just want to figure out what's the probability that I would get 17.12 or something more extreme or something greater. So what I would do is I'm going to locate 17.12 on my axis. We're going to kind of eyeball it first, and then I'm going to show you the really easy way to do it in StatKey. Okay, so 17.12 is probably, I don't know, somewhere around here. Okay, on mine, kind of in between the 15 and the 20. Okay, so there were a total of 1,000 dots. I only clicked my once, so I have 1,000 dots on mine. Maybe you have something different on yours. Okay, and I'm essentially, remember we, just like the cars, the red cars versus the total cars, we want to count how many of these dots were 17.12 or more. Okay, and then we can divide that by the total number of dots, and that'll give us the probability of getting 17.12 or greater. Now, when we do this by hand, which we're going to talk about in a minute here, like you're going to have to do on the exam, then we're actually really going to be drawing a line on our graph and actually physically counting those dots. Now, StatKey will count the dots for us. So to have StatKey count the dots for us, we're going to come up here, and because my alternative hypothesis said greater than, I'm going to click on right tail. So you click on right tail, and then you have to put the value of your original sample statistic down here in the box. So my original sample statistic was 17.12. So I'm going to click on that bottom box and put 17.12 in my bottom box there. All right, so when you do that, all the little X ones, okay, those are dots that were 17.12 or greater, okay? So they counted 18 of those on my graph, they counted 18. And then you divide by 1,000, and that would give me a probability of 0.018. Okay, so this little floating box here, that's what we're going to call our p-value. And remember, we said the smaller your p-value, the greater the evidence against the null hypothesis. A p-value, in this case of 0.018, says that if there really is no difference between tea and coffee, the probability that we would take a sample and get a sample difference that was 17.12 or greater is only 0.018. So it's a pretty small probability that we would get a sample statistic that is this large. So this actually gives us a pretty decent amount of evidence against the null hypothesis. Seems more likely that there actually is a difference between tea and coffee. All right, any questions on how you or what to click on or anything like that inside of StatKey? It'll make more sense as we do more of these. Okay, but you're going to load the data in. You're going to generate a bunch of samples. You're going to look at your alternative hypothesis to figure out which one of these three things in the upper left corner that you're going to click on. Okay, so if your alternative was greater than, you're going to choose right tail like we did here. If our alternative would have been less than, then we would click left tail instead. And if it's not equals to, then we click on two tail. Let me just show you the two tail real quick here.
Can you write that in the notes real quick?
It is written in your notes. Like, did you print
Okay.
out my notes pages?
Not this morning. Okay, it is in the notes.
Yeah, it's all written in there. Like, it's like step by step, already typed on there for you.
Great. Thank you.
All right, so on the two tail, remember also that once you click on these things, you have to enter in the value of your original sample statistic down here. That's something that people always forget. Okay, so I clicked on two tail. That would be if it was a two-sided test, then not equals to. Okay, and in this case, see that I have two little floating bubbles on the outside here. To get my p-value, I would actually add both of those together, because in a two-sided test, we're interested in distances of 17.12 or greater, or like, kind of negative 17.12 or lower. So we actually double, I call this area the tail area, this part over here. We're going to double the tail area in a two-sided test. So this is a randomization distribution for that same data that we looked at. This is one that I did, earlier when I was making the presentation. So you can see that it's a little bit different than the one that I actually got inside of StatKey. So there can be variation a little bit, but things should be roughly close. And if you guys were doing this on your own, which I hope you were, you probably got something slightly different than what I got in StatKey also. But hopefully your numbers should be similar. Okay, like 0.01 something or 0.02 something is probably what you should have gotten. And again, what StatKey is doing here is it's just saying, okay, this is just a probability. So I'm just going to count the number of values that were greater than or equal to my original sample statistic, and I'm going to divide that by the total number of samples to figure out that probability. So the probability is going to be in that floating box. It's what we're going to call our p-value.
On our test, you said that we're gonna have to count the dots, right?
Right.
So like, let's say we got 17.12 or whatever, can we just round it to 17?
On your sample statistic?
Yeah.
No, you should never
Or-
round, but you're looking for it on the, like, we'll show how to do some of the counting ones in just a second, but you're going to have to find 17.12 on this spectrum. So you're eyeballing where it is. So you might be eyeballing 17. It'll be fine. So like we said, okay, so if there really is no difference in tea and coffee on immune system, the probability that we would take a sample and get a sample difference that is 17.12 or greater is, based on this graph, is 0.026. So if you had something different for yours, because you could put that down on your paper too. Do I have this one on the paper? Oh, I do. So this is at the bottom of page 4 on your notes. It says, if there really is no difference in tea and coffee on the immune response, the probability we would take a sample and get a sample difference in means that is 17.12 or greater is 0.026, or 0.018 if you were following my other one, or if you have your own from your own bootstrap distribution. Okay, that's basically like the interpretation of what does the p-value mean. in this case. So the p-value is this 0.026, and this is what it means. It means that if there was no difference, the probability we would get a sample that has 17.12 or greater is whatever the p-value is. All right, so we're going to look at another example. So thinking back to Monday when we did our little ESP test, first of all, our hypotheses for whether or not ESP were real. So we had 5 different, in our class, we did letters. So A, B, C, D, or E. And so null hypothesis. So if there's no such thing as ESP, then we would expect that we would get 20% correct just purely due to chance, right? 1 out of 5. So, or 0.20. So P is the proportion of all guesses that are correct. And if ESP exists, then P would have to be greater than 1/5. So those were our 2 hypotheses. So does anybody remember what our sample proportion was from when we actually did the test in our class? You guys all went off into your little breakout rooms. You guys did amazingly well. We had 8 out of 16 people that said that they were able to guess correctly. So our sample proportion, p hat, was 0.50, 8 out of 16. All right, so 0.5 seems quite a bit different from 0.2, but is it enough different? How much evidence is this that ESP exists? Like, is this so much that we're willing to like go out there and like proclaim to the world ESP exists, and we were able to show it in our statistics class? Maybe you could write a book, Strike It Rich, something like that. That'd be pretty awesome. So in order to figure out how much evidence this is against the null hypothesis and in favor of the alternative hypothesis, then we would want to find the p-value for this test. Okay, so we're going to use StatKey to construct a randomization distribution again. Okay, so this time, what do I have going on here? How many and what type of variables do I have for this one? So I'll go back to I'll go find my chart.
Categorical, right?
Okay, I got categorical. How many?
1.
1 or 2?
Only number.
Only 1, right? So I have 1 categorical variable. Okay, so you can see that on here. It helps that we already had the hypotheses written out. So if I look on here, I'm like, oh, okay, that's how I wrote my hypotheses. That means that I'm looking at 1 categorical variable here. So what kind of graph would be good for this data? A bar chart. Okay, what did my sample statistic look like? We were looking at p hat. So we're looking at 1 categorical variable. So now I'm going to come back here to StatKey, and you guys pull up StatKey and do this with me. Okay, so in StatKey, now I'm looking at 1 categorical variable. So if I follow that line all the way over to where it says randomization hypothesis test, I'm doing a test for a single proportion. So in StatKey, back on the main homepage, where it says randomization hypothesis test, I'm going to choose test for a single proportion. All right, now when you're doing proportions in StatKey, you don't necessarily have to input the data. So there are some data sets that are already in here, but the data basically consisted of the number of successes and the number of trials, 8 and 16, which is really easy to enter yourself. So most of the time for categorical data, either 1 or 2 categorical variables, you're going to enter the data yourself just by clicking on edit data. So I'm going to click on edit data. All right, and we had 8 people that guessed correctly out of 16 total people. So I'm going to put that in. Okay, then you can see under original sample, it says 8, 16, and then it gives us the sample proportion of 0.50. All right, one thing that we have to really watch for is making sure, remember, all these randomization distributions are constructed assuming the null hypothesis is true. So we have to make sure that StatKey knows what the null hypothesis is. When we're comparing 2 means, like we were last time, there's only 1 option for the null hypothesis. So StatKey already knows, okay? But in a test of 1 mean or a test of 1 proportion, like we're doing here, we have to tell StatKey what the value under the null hypothesis is. So see here where it says null hypothesis, right? The default is 0.5, but what was our null hypothesis? I'll write it up here. So we had null hypothesis was
1/5.
P equal to, 1/5, which is 0.20, right? And then the alternative was that P greater than 0.20. Okay, so my null hypothesis is P is equal to 0.2. So see the little box where it says, so it says null hypothesis P equals, and then click on that box and change it to 0.2. You always have to enter this as a decimal number here. Okay, so now I have the correct null hypothesis. Now I'm going to generate my randomization distribution. Okay, so StatKey is going to simulate samples, assuming that the null hypothesis is true. So it's simulating samples based on P equaling 0.2. So if the null hypothesis was true and I was taking samples of size 16, these are going to be all the different possible types of values that I could get here. All right, so you can click on it. I'll reset my plot. Even 1,000 samples, there's so many dots like in these little spiky things because we only have a sample size of 16, then it's not going to show it very good. Also, this is slightly skewed here, again, because of our small sample size. So results might not be ultra reliable here. Okay, but just so we can get the process down here, I've created my randomization distribution now. And what should I click on? Should I click on left tail, two tail, or right tail?
Right tail.
Right tail, right? So greater than is right tail. All right, so greater than is right tail. So I click on right tail, then down in the bottom box, and people forget this all the time. So don't be one of the people that forgets it. Okay, in the bottom box, I have to put my sample proportion. So my original sample statistic. So I'm going to click on the bottom box and put in 0.50. All right. Then this is a one-sided test. So the floating box here is my p-value. So my p-value is 0.004. Remember, the smaller your p-value, the greater the evidence against the null hypothesis. So our p-value would be 0.004. Again, this is not exactly symmetric. This is definitely more on the skewed side. And this method does require that we have a symmetric distribution here, or pretty symmetric. So this isn't, so I probably wouldn't start publishing any papers about the existence of ESP based on the results of our class data here. But for practice purposes here, we're going to use this as our p-value. So that's pretty small, seems very unlikely. Okay, and if you look at our picture here, you can see that this is way, way, way out there. It seems like very unlikely that we would get a sample statistic that was 0.5 or greater if there really is no such thing as ESP. All right, so if we wanted to write down kind of an interpretation sentence about the ESP study, okay, then our p-value was 0.004, right? I think it was 0.004. So this means that if ESP does not exist, the probability we would take a sample and get a sample proportion that is as extreme or more extreme than 0.5, because that's what we got in our sample, the 8 out of 16, is only 0.004. So it's pretty unlikely that we would get this sample statistic purely due to chance if the null hypothesis is true. All right. So now we've looked at doing a couple of these in StatKey. Let's look at how we would do this by hand, which basically we're doing the same thing by hand. It's just that instead of having StatKey count the dots for us, then we're going to have to count the dots ourselves. But it's essentially the same process. Okay, so this when you do it by hand, you're going to be given a randomization distribution. You're going to have to look on the x-axis, find the value of your sample statistic, draw a line, and then you're going to count how many dots are more extreme than that line. Okay, if If it was a one-sided test, then meaning it was greater than or less than in the alternative, then your p-value is going to be equal to this tail proportion. And if it's a two-sided test, meaning that you had not equals to in the alternative, then the p-value is 2 times the tail proportion. So here's an example here. Okay, so here's, this is another randomization plot, still for the T and immunity example here. Okay, so remember my original sample statistic was 17.12. So I'm going to look on the x-axis and I'm going to draw a line for 17.12. Okay, so I have to look, I have to say, okay, here's 10, here's 20. So it's going to be slightly more towards the 20, not quite halfway, a little over halfway there. Draw a line. Okay, then I'm going to count the number of dots that are as extreme or more extreme than my value here. So by extreme, we mean like on the outside. So we're always going away from the center when we're counting dots here. So on my picture here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I had 13 extreme dots. And if I look up here, I can see that for this one, we had 500 samples. So if I take 13 divided by 500, then I get 0.026. Okay, this 0.026 is my tail proportion in a one-sided test, meaning greater than or less than in the alternative. Then my tail proportion is my p-value. If it would have had not equals 2, then we would have had to double the tail proportion to get my p-value. This one was a one-sided test though. So my p-value 0.026, okay, which is basically what we found what it was before when we had StatKey do it. Okay, questions about how we do that by hand? We're going to look at a couple of examples, a couple more examples here, get a little bit more practice. Oh, I actually had that written on there. There we go.
What if we have to do a two-tail?
We'll show an example of a two-tail here. So in a two-tail, you do everything the same, only once you get your tail proportion. So this 0.026, I would multiply it by 2 before I called it the p-value. So we're looking at a couple examples here. One is another one-sided example, and then the other one is a two-sided example. So we'll get practice with both of them here. So here is a randomization distribution. It tells us that the null hypothesis was mu equals 80, alternative mu greater than 80. There's 300 dots on this randomization plot here. And my sample mean was 91. Okay, so in order to find the p-value on this, then I'm going to look on my x-axis for my original sample statistic. So I'm going to look for 91. Okay, so look and see where 91 would be, or where we think 91 would be. And you're going to draw a line. All right, once I draw my line, I'm going to count everything that is as extreme or more extreme than wherever you drew your line. Okay, so I'm going to count all these dots here. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Okay, so I got 32 dots. And if your line went over this dot, maybe we should really call that 33 because we're looking for as extreme or more extreme. So I'm going to call mine 33 dots since it went on top of that one there. Okay, and I'm going to divide by the total number of dots, which was 300. So 33 divided by 300 gives me 0.11. So this is my tail proportion, but I had a one-sided test. So in a one-sided test, a one-sided p-value That's just equal to the tail proportion. So in this case, my p-value would be 0.11. All right, let's look at another example here. So this one, my null hypothesis, mu1 equals mu2, alternative mu1 not equal to mu2. This one's based on 1,000 randomization samples, and my difference in sample means was 6.88. Okay, so again, I'm going to look on my x-axis and say, where is my original sample statistic? So I'm looking for 6.88 on the x-axis here. So I think 6.88 is around here. Okay, this one we have like something like that. So we have 5.5, 6, 6.5, 7, 7.5. So I think 6.88 is right in there. Okay, so I marked 6.88. Okay, now I'm going to count the number of extreme dots. Okay, and I'm going to have, so my tail proportion is going to be the number of extreme dots over the total number of dots. So how many extreme dots do you count there?
About 8, right?
Yeah, 8 is what I got too. So 8 looks good. Okay, and we can tell how many total dots we have here by looking at the number of samples. So we had 1,000 in this case. So my tail proportion would be 0.008. Okay, this is my tail proportion. This was a two-sided test. I can tell it's two-sided by looking at the alternative hypothesis. If the alternative hypothesis says not equals, then it's a two-sided test. So I need a two-sided p-value for a two-sided test. So my two-sided p-value is going to be 2 times the tail proportion. So that's going to be 2 times 0.008, which is 0.016. So my p-value in this case would be 0.016. So just a couple more comments about understanding the p-value, okay, and what it means. So we defined the p-value earlier as the probability of obtaining a sample statistic that is as extreme or more extreme than that actually observed if the null hypothesis is true. So kind of interpreting what does a p-value mean, we've written that out as if there really is no difference between the effect of tea and coffee on immune system response, the probability of getting a sample mean difference of 17.12 or greater is 0.026. So just kind of looking at how this relates to our definition here. So remember, a p-value is always computed assuming that the null hypothesis is true. Okay, and our null hypothesis for the tea and coffee said no difference between tea and coffee on immune response. So if the null hypothesis is true, that would mean that there really is no difference between tea and coffee on immune response. P-value is a probability, but it's a very specific probability. Okay, it's the probability of getting your sample statistic or something more extreme. So in the case of the tea and coffee, it would be the probability of getting a sample mean difference of 17.12 or greater. And then the value of the p-value in this case was the 0.026. So that's what that 0.026 means. Okay, and then also remember that we said that the smaller your p-value, the greater the evidence against the null hypothesis and in favor of the alternative hypothesis. So now, so far, we've talked about step 1 of doing a statistical test, which is state the hypotheses. We've talked about collecting the data, computing the sample statistic. Now we've talked about examining the evidence, and we know how to find p-values. There's one last step for our statistical test, and that is to draw conclusions. So we're going to draw conclusions based on that p-value because the p-value is the evidence. So next time in section 4.3, then we're going to talk all about how to draw conclusions based on the p-value. What kind of conclusions can we draw and how to word those conclusions? Just like with with our confidence intervals, how we talked about how the wording of interpreting that confidence interval is pretty important and can make a big difference. Same thing with hypothesis tests. So we're going to talk about how to do that.